Hello everyone, welcome to this short tutorial on linear approximation. We begin with warm-up. The question reads, write an equation of the tangent line to the graph of a function f of x equals x cubed minus x at a point 1, 0. Then we'll verify our results with a graphing calculator. First step, we take the derivative of f of x and then we evaluate it at 1, which gives us 2. And then in the point slope form of the equation of the line, we set up our tangent line equation, simplify, and we obtain y equals 2 x minus 1 parenthesis. We want to use a graphing calculator now to verify our point of tangency and the graph of the function. So this is functions in y1, y2 for f of x and then the tangent line. So let's graph and see. Now we want to verify that the point of intersection of the tangent line and the graph, which is the point of tangency, it actually corresponds to what was given in the question. So let's trace at 1 and see what the output gives us. And we see the y coordinate at the point of tangency is 0, which corresponds to the point of tangency in the question. Now let's go back to our slide. Okay, we'll take a look at some graphical exploration of tangent line and the function at a point of tangency. It is important to note that based on exploration, we can determine how good of an approximation we would have with a tangent line if we want to evaluate function values. So let's go to this link here and see what Desmos offered. So in Desmos, we're able to evaluate the function and the tangent line at selected points, as we can see over here. So this is our point of tangency here. If I evaluate this function at, say, 1 point, this is 1.2. So if we go to 1.2, we see the difference between the tangent line value and then the function value. Now, even if we get closer to the point of tangency, we want to verify what's going on. Is the value out of the function approximately equal to the tangent line function? Are they getting bigger as we move away from the point of tangency, or are they getting closer together as we move away from the point of tangency? And so if we track any point maybe in the tangent line, let's put, say, 0, let's say 1.1, and then we'll find the point of tangency is very close to this point we value. Now you can see what is the value of the function, the output in the tangent line, and the output and the function. We find 0.231 and then 0.2. That is a very close estimation of the function value. And so based on this exploration, we can conclude that the closer we get to the point of tangency, the better our approximation will be to estimate the function value. So next we want to look at some example. Before the example, let's first look at the definition of linear approximation. Say a function. If f is differentiable at x equals a, then the linear approximation of f at point a, f of a, is a linear function derived from the point-slope form of the equation of a line. In other words, we say linear approximation is the process of estimating a function value f of a by using the tangent line equation, such that f of a is approximately equal to L of a, the linear function, or the tangent line function as x approaches a. We say, note that by restricting the values of x sufficiently close to point A, the values of y or t of x can be used as approximation of values of the function. In other words, the limit as x approaches a of L of x will be equal to f of a. So see diagram below illustrating the function, the tangent line, and then the point of tangency. Next, we look at a problem, first example guided practice, and we say given f of -3 equals 4 and f prime of -3 equals 2, find the linear approximation for f of x at -3.1. So how do we approach this problem? First, we need to set up our equation for the tangent line, and then once we find the equation of the tangent line, we can use the tangent line equation then to evaluate the function value or the function at -3.1. So in here we substitute 3.1 into the function, which would approximately be equal to the tangent line output at -3.1. Our result is 3.8. If you have your graphing calculator, you may evaluate the function at -3.1, and we'll see how close those two values would be. Our second guided practice has to do with a cube root function, more like an application. So we're using the cube root function values. Instead of evaluating the cube root, we're using the tangent line equation to evaluate the cube root of 63. So we take our derivative and then substitute 64 into the derivative, gives us 1/48. And then we write a tangent line equation. Then we evaluate the function at 63 using the tangent line equation, which gives us 3.979. Next, we have some independent practice problems, which I say take a minute and solve it, and then I'll return and we'll discuss our solutions. Okay, now let's go to look at our solution for practice 1. So here we see we take g of -1, which gives us an output of 1, and then the derivative g prime 2x plus 1 we evaluate at -1 gives us -1. So we write our tangent line equation, and then now we're able to evaluate the function at -1.2 using the tangent line equation, which then gives us 0.2 as our output. Our second practice problem here says we again find the function value at pi/8, which gives us 1/2, and then we take the derivative and evaluate at pi/8, which gives us -2. So now with our slope and then our y, f of pi/8, we're able to write our tangent line equation, and then we use the tangent line equation now to evaluate f of pi/4, which then gives us our result 2 minus pi/4. Keep practicing. This is the end of our tutorial, and as always, thank you for watching.